Hello again, class. We're going to finish section 3.1 now, talk about the last part of this section, which deals with applications. And so we're going to start here in the application section. And there's a few of them that we'll walk through. The first one is this idea of measuring arc length. And hopefully, when you go back to the definition with regards to the definition of an angle, you could see that we could do just a little bit of simple algebra to get to the equation of arc length. And the arc length is defined as the S value is the radius times the angle. And the theory behind this one is illustrated here in this figure 1.12. So the idea that we have here is that we have a circle with a radius of 4. And we have an angle there of 240 degrees. And so when you want to do this calculation with regards to that, we had the equation S equals R times theta. And basically, just to redraw this circle here a little bit, this was 240 degrees, and the radius here was 4. So when we do this calculation, remember that, say like this was 4 inches. So when you want to measure the S value, which is the distance traveled from this point all the way around to this point, you also want that to be in inches. And again, remember what I alluded to at the beginning here is radians is a dimensionless quantity. So if you do 4 times degrees, you're not going to get inches over here for the arc length. So the first thing that we'd have to do this calculation is to convert the angle into radians. So that would be 240 degrees. And then we have pi on the top, that's in radians, and 180 degrees on the bottom. So the degrees cancel, right? And you could see here that a little bit of manipulation here with regards to fractions. As you could see that 60 goes into both 240 and 180. 60 goes into 180 3 times, and 60 goes into 240 4 times. So the angle in radians would be 4 pi over 3. So now to calculate the arc length of going around S, say like it would be 4 inches times 4 pi over 3. So with regard to that, you could leave it in this crazy form where we have pi involved with it, right? 4 times 4 is 16. But, you know, in the real world, you would want to give a value. So if this is inches, for example, you would just get out your calculator. You could plug in 3.14, and let's round it to 2 decimal points. And if you did that, you would get 17.76. So that is the first application, talking about arc length. So let's do one more, because this one's a little bit I don't want to use the word strange, but I kind of want to with regards to that. Because when I read this one, I actually had to look this word up. So this was a problem that I saw in the book. It says the arc length of 125 meters subtends, and you can see I have it in red, this angle in a circle of radius of 25. So basically what that means, what subtends means is that's actually the arc length. It's the value that goes all the way around the circle. And so if you think about that idea of the arc length, excuse me for pausing there for a second. It would look like this. So let me clear this up. There we go. And so if we talk about that, if this was 25, that would be the radius, 25. You could say that this would be all the way, say it stops around there. That S is 125. And so to do the calculation to find theta, you would have S over R. And so that would be 125 divided by 5, divided by 25, excuse me. And that would be 5 radians. When you read the problem, they were asking you to calculate that in degrees. So you just have to do the conversion, right? So you have 5, and then in this case, it would be 180 divided by pi. So if you did that, that would be 900 divided by pi. And so you get out your calculator, and this says round it to 1 decimal point, according to what the problem asked. So you would get a number of, say, 286, and then it was 476. And so that 7 would increase that 4 to a 5. So the answer would ask you is 286.5 degrees. And I do want to point out that when you read some of these homework problems, you will want to be able to make sure that you read the problem, and they'll tell you if they want a decimal form, what to round it to. And I'll tell you, when I do these problems, before I give them to you, the biggest mistake that I have is I don't read them very closely. And I would type in, instead of the 286.5, I would type in 286.47, and they would mark it wrong. So even though that feels like you're doing the problem correctly. So just beware of that aspect of it with regards to that. Okay, so the second of the applications that we will be talking about is this idea of speed. And we have 2 different kinds of speeds that we're going to talk about. The one speed that we all know and love is linear speed. For those driving a car, that would be miles per hour or feet per second, etc. And so we're, I think, all familiar with that. But now, since we're introducing this idea of angle, we're actually going to introduce another speed, which is called angular speed. And so linear speed is defined as the arc length divided by time, right? And so that's a distance, right? So for example, if the length was in miles and t was in hours, that's where we get our miles per hour. Here, on the other hand, we have this angular speed, which is defined by an angle measured in radians divided by time. So angular speed is a little strange in the sense that the units are radians over time. And so we're going to show some relationships with regards to that. And here in this next slide is probably the most important relationship with regards to this. And I'll show you what I mean. And I'm going to do this, walk you through this on the whiteboard. But first, I want to read you the problem. Well, here we have the relationship, the velocity, which is linear velocity, is related to the radius times the angular speed. And so with regards to this calculation, we're going to use that for this. So it says a woman is riding a bicycle whose wheels are 26 inches in diameter. And if the wheels rotate at 125 revolutions per minute, find the speed that she's traveling. And we're going to do it in miles per hour, right? I mean, that's what our speedometer in our car. And when I look at my Apple Watch as I'm riding my bike, it gives me the speed in miles per hour. So how do we do this calculation? Well, let me pull up the whiteboard here. And let's walk through this a little bit. Okay, so we have the idea of this tire, right? Or wheel. And the wheel has a diameter of 26 inches. So the diameter is from one end to the other where it passes through the center of the wheel. So what is the radius? That would be half that. So the radius here would be 13 inches. And so first thing we could look at is that we have the equation defined as the linear speed is defined as the radius times the angular speed. So if you think about it, there's one way that a speedometer could actually work in your car is they could measure how fast your wheels are turning, right, with regards to that. So what does revolutions per minute mean? So what does that mean is that every revolution that this wheel turns, right? And so in this case, if you got out your stopwatch and you counted how many times this wheel ran around, it basically would have to go around 125 times in 1 minute. And so that's what we mean by revolutions per minute. You know, the wheel will be traveling, say, in the counterclockwise direction with regards to that. So to do this calculation, first thing we need to calculate is the angular speed because we need W, right? And W is defined as theta over T. So to get that calculation, first thing we need is the idea of this angular speed, right? Well, with regards to T, it is 125 revolutions per minute with regards to that. And so to calculate this aspect of W, what we need is that when you're traveling around with regards to the angle, right? And you're going around and around 125 times, what would be the angle? Excuse me, that wasn't T. This is revolutions per minute, not T. I'll apologize for that. So we're going around and around 125 times. So if you think about it, what is this angle? Well, if you go around one time, that's 2 pi. If you go around two times, that would be 4 pi. And again, we're talking about it in radians. If we're talking about degrees, it would be 360, 720, et cetera, et cetera. So the angle theta is going to be 2 pi, and then how many times it goes around? And it goes around 125 times. So if you do that calculation, you would get 250 and pi, and our time is in minutes, right? Because it's revolutions per minute. So if we think about theta, it's 225. And if we divide by t, we would get minutes. So our W is 250 pi in the minutes. So far, so good. So now we want to get linear speed. And so if we take a look at the linear speed, and I'm just going to get the eraser out here. Oops. Get rid of a few of these things here. I'll leave my wheel up there. So with regards to linear speed, we have this equation right here. And so this would be 250 pi over minutes. And then we're going to multiply it times 13 inches. And so when you do that calculation, you would get 3,250 pi. And now we're in inches per minute. So again, that's not a typical way that we talk in real life, that we are traveling inches per minute. We typically talk about miles per hour. If you're doing some scientific calculations, if you a lot of feet per second you hear, or meters per second. So those are the ones that you'll hear in the applications in the real world. But when we want to convert, let me walk you through this calculation. So right now we have, and then pi, and then we have inches on the top and minutes on the bottom. So we want to convert inches into miles. And so I remember, or you could look it up, that, and the good news is everything's going to be open book, so you can look everything up. So you could look up the conversion factor from inches to miles. But for some reason, I remember that there are 12 inches in 1 foot. So you see how I wrote the ratio, where because I put inches on the bottom, these inches cancel. And then I remember that there are 5,280 feet in a mile. So again, we want the feet to cancel out. So since feet's on the top, I'm going to put this factor of feet in the bottom down here. So you can see feet cancels here and feet cancels here. And I also remember 1760 yards is in a mile as well. Don't ask me why I remember those crazy things. But again, you don't have to remember these. Just look them up and use those conversion factors. And so the last one you would take, and you want to convert minutes into hours. So since the minutes are on the bottom in this case, we'll put 60 minutes on the top. And there are 60 minutes in 1 hour, right? So you cancel these out. So here's, you definitely need a calculator. You have to plug in 3250, multiply it times pi, divide it by 12, divide it by 5280, and then multiply it by 60. And if we round to the 10th, I ended up with 9.7 miles per hour. So not a super fast rider there. My wife and I like to take rides on the lakefront path, one of the few things that you can do in this pandemic. And our average is around 14, which we pass some people, but we get past a lot as well with regards to that. So the last thing we're going to talk about is this idea of calculating areas now and using an angle measurement. Back in your geometry days, you talked about measuring an area of a circle with just the radius. Like the area of a circle is pi r squared, and if you wanted a quarter of that, you would divide it by 4, et cetera, et cetera. So in this case, instead of doing that, we've have this equation of area, which is 1/2 the radius squared times the angle. And so if you take a look at this relationship real quick, right? So say like we have this circle. And we're saying that the area is 1/2 r squared theta. So when you do this, if you remember from your geometry days, the area of this circle was pi r squared. And so what is the area? The area is the whole circle. And so if you think about what is the angle of the whole circle? Well, the angle is that you go all the way around one time, right? So that would be 360 degrees, or it would be 2 pi radians, right? So if I plug in 2 pi in for theta, you could see that the area would be 1/2 r squared, 2 times pi. And these two would cancel. And you see you get back to our geometry approach to calculate an area, which would be pi r squared. And so I'm going to leave you with one last problem, and this is probably one of the most important problems for a college student that doesn't have a lot of money, is figure out the best buy for your pizza. So here I have a scenario of these two pizzas where the large pizza, 16-inch, is $15, or there's an 8-inch diameter pizza where you can get 2 of them for $7.50. So which one is the better buy? And by my definition, the best buy pizza is the most pizza you could eat for the least amount of money. And so how do we do this calculation? Well, let me kind of show this to you on the whiteboard, and this will be our last problem. So the idea is, let me clear here, is that we'll have one pizza. And then remember, diameter is, this is 16 inches. This is the large. So this radius would be 8 inches. And this would be $15. Or you have 2 8-inch diameter, right? So if this is 8, the radius would be 4 inches. And so both these pizzas would be $7.50, and this one would be $7.50. So each one you're spending the same amount of money, $15. So you can get 2 mediums for $15, or you could get 1 large for $15. Which one's the better buy? Well, let's do our area calculation, because basically when you're eating pizza, you're eating the area of the pizza, right? The idea of eating it, you're not just eating the circumference, etc. So again, going back to our new formula here, right? R squared theta, where theta is, you're going all the way around. So this theta would be 2 pi. So when you do that calculation, we get back to our pi r squared again. So let's plug these in. So we have pi, and so this for the large one, let me put L down here. That would be 8 squared. So that would be 64 pi square inches. So one large, you get 64 pi square inches of pi. And if you plug that into your calculator, that's about 201 square inches. So what about the medium? So that again would be pi r squared. And you plug that in, you would have pi. And then in this case, our r is 4. So here we have 16 pi square inches. And if you did that calculation, it's about 50 inches squared. So since both the values are the same, right? But remember, we have 2 of these. So if you take a look at this, the large for 15 bucks, you have 201 square inches, and 2 mediums for 15 bucks, you have 50 times 2, where you only have 100 square inches. So you can see that because the values are exactly the same money-wise, the large one is twice as good a deal as the small one. And that typically is the way it works, is that you could see that the square term here really makes the radius of the pizza quite important in the aspects of the overall area. And so most of the time when you go in and buy a pizza, the large is always the better deal with regards to that. In my household, my wife and I like a little bit different stuff on our pizza. I'm actually an anchovy guy. My wife hates it. And so if we end up getting different pizzas, it's not, I know it's not as good of a deal, but it keeps everybody happy because my taste buds and her taste buds are a little bit different. So that ends section 3.1. I hope this worked out all right. I'm going to stop the recording now. Have a great day.